going to take a look at the properties and the reaction of alcohols in this video. First of all, if we take the structure of an alcohol and we look at two alcohol molecules which are close to each other. So there's one of our alcohols, here's the second. So in this diagram now we have two methanol molecules. Notice how the carbon and the oxygen have to be bonded together. So in the first methanol molecule we've written H3C. It's fine to do this way. Whereas on the second one we've written CH3 for the direction in which the bond is looking. When these molecules come close together, because they have oxygen and hydrogen as a covalent bond within the molecule, molecules that are close to each other can form a hydrogen bond. This means that alcohols have got quite a high melting point and boiling point. If we consider them with water, their boiling points and melting points are a little lower. However, from methanol, if you compare that with something like methane, methanol would be liquid at room temperature, whereas methane is a gas at room temperature. Now, alcohol molecules readily dissolve in water. However, as the chain gets longer, the molecules themselves become less soluble in water. This is because on our molecule we have two ends, and this goes for all molecules that have a polar end and a non-polar end and usually dissolve in water. This is our polar end. Our polar end is known to be hydrophilic. Because it's polar, as is water, it readily dissolves in water when water acts as a solvent. On the other hand, as the chain gets longer, we have this organic end which is termed hydrophobic. And our hydrophobic end of our organic chain is non-polar. As the hydrophobic part of the chain increases in size, it's more difficult for the molecule to dissolve in a polar solvent such as water, whereas the short molecules such as ethanol, methanol, propanol will readily dissolve in water. As the chain gets longer for the hydrophobic non-polar end, they become more and more insoluble. We're now going to take a look at some of the reactions of the alcohols. The first reaction we're going to look at is the reaction of an alcohol with sodium. Now, during this reaction we produce an alkoxide, which is an anion, and we also produce hydrogen. So let's take a general equation for this. Now, if you remember, we can use R as our alkyl group. So a general equation would be our alcohol, ROH, plus sodium going to make our alkoxide, and hydrogen. Now, because our alkoxide is soluble in water, we can label it as RO negative Na plus, or we can label it as two separate entities and make them aqueous. Let me just show that as a little example just below. So we could end up with this as our products. So let's give an actual example with a real alcohol molecule now. So let's simply take ethanol. So notice the stoichiometry isn't going to change no matter which alcohol we use. So it's always 2, 2, 2 and then 1 hydrogen at the end. So if we take ethanol, which starts off in its liquid form, we react this with sodium, and we must remember there are 2 sodiums. We go to make our alkoxide and hydrogen. Our alkoxide is called sodium ethoxide. It's important to note, as we move from primary to secondary to tertiary alcohols, the reactivity decreases. If we use oxidizing agents such as potassium permanganate or sodium dichromate, we can oxidize our alcohols depending on whether they're primary or secondary. We cannot, however, oxidize a tertiary alcohol. The full extent of the oxidation will be covered in the relevant videos for aldehydes and ketones. But first of all, primary alcohol primary alcohol will be oxidized, and we show this by putting an O in square brackets, to form an aldehyde. As I said, this will be covered in more detail in the aldehyde video. The general equation for this is simply RCH2OH in the presence of an oxidizing agent will go to form RCHO plus H2O. A secondary alcohol in the presence of an oxidizing agent will go to make a ketone, and this is covered in more detail in the ketone video coming up. The general equation for this reaction is RCH OH R dash. Remember, R is an alkyl group, R dash is the other side of the alkyl group. Remember, for a secondary alcohol, the hydroxyl group must be in the middle of the chain and not have a methyl group attached to the carbon. That would make it a tertiary. This in the presence of an oxidizing agent, once again O in square brackets, would go to make RCOR. Now, in this molecule that I've just described here, if I draw this out a little bit better than what I've got, this means it's RC, double bond to the oxygen, then the other alkyl group. This also, in the reaction, produces H2O. With the primary alcohol, it's also possible that in the presence of a strong oxidizing agent, that the primary alcohol will oxidize to form a carboxylic acid. This means the alcohol will oxidize to an aldehyde, and the aldehyde will further oxidise to a carboxylic acid. With a strong oxidising agent, it's likely to happen all in one go. Now, it's important to remember, because this can be coming up as observations, and with observations we have dichromate. The colour change for dichromate is orange to green, and for the permanganate ion it would be purple to pale pink. There's another reaction of the alcohols called esterification, and we'll look at esterification when we do esters in the future.